Returning to our discussion on instantaneous power, we were contrasting single phase and three phase. Now we're going to formalize that understanding before moving on. The instantaneous power, that is, the power as a function of time, in a network with some voltage and some current, is defined as inputting our time-varying functions for voltage and current, and knowing the following rule, we get the following. The important part of this analysis is that the instantaneous power has an oscillating part and a constant part. The first part is the double frequency cyclic power whose average flow from source to load is equal to 0. The second part is the average, or active power. This can be proved mathematically by evaluating the integral of the power function above for all time. This second part can be rewritten as follows. Note that the first two terms are the RMS voltage and RMS current. They're followed by a term denoting the phase shift between the voltage and the current. This phase shift we've just formalized is very useful in understanding the impact of circuit components. That's because the phase shift between voltage and current in a given network is the same as the angle of the total impedance. It is otherwise known as the power factor. The power factor will be the same whether the current is lagging or leading the voltage. Remember, cosines don't care about whether an angle is positive or negative. It returns the same result. Therefore, these terms are used to describe the circuit. Convention states that the power factor is taken positive when the current lags the voltage. Here's a voltage waveform, and here's its matching current. You can clearly see here that there is some amount of lag between the two signals. In this case, we have a lagging current, meaning it's an inductive load. Here is the phasor diagram. If you remind yourself of the phasor diagram of an inductor, you will see the positioning of the current and voltage phasors as a clear indicator that this is correct, with the current lagging behind the voltage. Please note that the reverse is true with capacitive circuits, where the current leads the voltage. This leads us directly into reactive power. Remember the formula for instantaneous power containing both an oscillating and constant part? Revisiting that and doing some further analysis, there's a lot of numbers here, but I want you to realize something important. The first term, cos, will always be 0 for inductors and capacitors. The second term, sine, is the cyclic power between supply and load with an average of 0. This power flow represents the reactive power Q, and it is a continuous transfer of stored energy between the inductive and capacitive elements of the grid, with capacitors generating and inductors consuming reactive power. This does no useful work, but cannot be avoided. Reactive power is the power that magnetic equipment, such as transformers and motors, need to produce the magnetizing flux by which they operate. The expression for reactive power is given by the unit of reactive power is the volt-ampere reactive, VAR. So, to recap, we've learned so far in power that instantaneous power boils down into two different types: active or average power and reactive power. The first is a continual transfer of active power, and the second is purely oscillatory and does no useful work. This brings us to the unifying concept of complex power. Complex power is defined by S being equal to V multiplied by the complex conjugate of I, where V and I are the phases that we've encountered before. This formula can also be expressed as, or alternatively, you may have noticed that we've multiplied by the complex conjugate of the current phasor. We do this in order to preserve the argument. If you multiply complex numbers, the arguments, that is, the angles of the phasors, are added together. For our purposes, however, we are interested in the difference between the voltage and current angles. Therefore, we require a difference, so we negate the second argument by multiplying our voltage phasor by the conjugate of the current phasor. We can also express this equation in rectangular form. Here, we can see the real part of the complex power to be the active power, P. We can also see the imaginary part of the complex power is the reactive power, Q. The magnitude of the complex power is called the apparent power, and its unit is volt-ampere. It is called the apparent power because, useful or not, that is the power that is perceived in the network. Note that the apparent power can be equal to the real or active power, but only in the complete absence of reactive elements in the network. We now have the three ingredients for our triangle of power: active, reactive, and apparent power. They can be visualized in the following way. A helpful way to think about the interplay between these different types of power is to picture yourself pulling a cart along a rail. You're slung out to the side, so what that means is you have to use a rope in order to pull the cart along. But not all of the force, the apparent force that you're putting in, is actually contributing towards the movement of the cart. There is some wasted because you are off to the side. This is exactly what reactive power is. Force that must be exerted, but doesn't actually do any noticeable or useful work. Meaning that the apparent load on yourself is higher than what it ought to be if you are pursuing the most efficient movement process.